When we get into more complicated chemistries like kinetics and thermodynamics, which we'll talk about next semester with Dr. Eric. But for this part of the semester, for our part of the semester together, we only use simple algebra. But here's the thing. The reason why we go through chapter 1 is to hopefully set a pattern of using dimensional analysis in a way that's helpful when we get into more complex topics. Right now we're going between grams and pounds. We're going between inches and millimeters. We're going all these things, right? That's what we're working through if you're working through your achievement. Where we're headed with this is we're going to change from very common things like inches and millimeters or pounds and kilograms to weird things like grams and moles. So that's why we set a foundation on doing some of this dimensional analysis up front, so that when we do jump into chemistry terms, we have the foundation in math to do dimensional analysis associations. Because here's the aha, here's why we're doing all this dimensional analysis stuff that some people think might not be that exciting. And to be honest with you, most people in this class are probably pretty comfortable with dimensional analysis. And that's why we do this. So if I'm gonna go from grams of compound A to grams of compound B, I can't directly go that direction. It doesn't work, right? This is called the law of stoichiometry. It won't work. I can't go from grams of A to grams of B. It's absolutely irrelevant because they have different compositions, so they're not equalities. So what I have to do is I have to go through a series of dimensional analyses to go from grams of A to moles of A, moles of A to moles of B, moles of B to grams of B. Okay, so this is where we're headed. This is what we want to establish and build this semester, is an understanding of chemistry dimensional analysis. This gets complicated because now all of a sudden I can do this several different ways. I can do it from solid to solid, I can do it from solid to liquid, I can do titrations. We call these different things, but what we're really doing is we're going through a dimensional analysis. And so we set the foundation, or we establish a foundation in understanding of simple terms like inches to millimeters. Okay, so that's why we go through this exercise of teaching dimensional analysis through kind of a non-chemistry chapter. We will be quickly getting into chemistry, again, using funny things like grams and moles, that's kind of weird, and moles and grams. Okay? And then finally, we're going to go from grams to molecules of B, all right? Or molecules of A. And here's the thing. Each of these arrows up here is a dimensional analysis. It's a relationship. So this problem would be very complex. It would be 1, 2, 3, 4, 5 calculations to go from molecules of A to molecules of B. Okay? So that's why dimensional analysis is set a foundation in this to understand it's very important. So to know how to set up the problem becomes the problem. Do I set it up this way, or do I set it up this way? Do I set this one up this way or this way? This way or this way? So that's why we go through this. Some of you probably did like the box method or whatever it is, that you have this big long string of things like this, and your teacher said, okay, here's where we start, here's where we're ending, and so you cross, and you end up, you can't cross them all out. And you set them up in these boxes and you cross them out. So that's what we're doing today. We're learning how to set up these equations using dimensional analysis. Okay? So that said, the conversion factor is a known ratio. The conversion factor is a known ratio. If it's something that I haven't asked you to directly memorize, you'll have a table. Even on our standardized final in here, the ACS, American Chemical Society final, we have a table that you're given, because we don't ask you to memorize all these. Why memorize something that you can find in a table? If it's knowledge that you need at your ready, like 273.15, we should have that memorized. Okay, not have to look back through what's the conversion in centigrade and Fahrenheit, or in Kelvin. Okay? So for the most part, these ratios will be given to you or provided for you. On the worksheet today in class, it's provided for you so that you can just use it, so you don't have to find the table inside your book. Okay? So that said, let's break this down and see how this works, because it's actually kind of fun. These are, some of you that have done these, they're kind of fun puzzles. Okay, so let's, for an example, say that we want to convert feet into meters. Feet into meters. I want to convert feet given into meters unknown, not known. So I have a known and I have an unknown. That's where we start. So we start with what we know. So what we know is what we know. What we don't know is what we don't know. So we start with what we know and we end with what we don't know, hopefully. And if we have the right ratios, the right factors here in our boxes, we're going to be able to go from what we know to what we don't know. Okay? Again, that's the whole goal of dimensional analysis. So I know that 1 meter equals 3.281 feet, and that's been rounded off. It keeps going. All right? So 1 meter equals 3.281 feet. It's not an exact number. It's an approximation. Notice the aha here. 3.281 feet equals 1 meter. 1 meter equals 3.281 feet, meaning I can put that ratio this way or this way in my dimensional analysis. It goes both ways. I can either have the one on top, I can put feet on top or meter on top and feet on the bottom, or I can put meter on top and feet on the bottom. Okay? What drives it is what? What I know. Okay? In this case, what do I know? I want to go from feet, I know feet, and I want to go to meters. Okay? Again, I'm setting this up, I'm going slowly because some of this might be like a refresher. Others I think you're like, got it. Okay? So feet to meters through a ratio that I know. Thus, 1 meter equals 3.281 feet, or 3.281 feet equals 1 meter. So you could almost think about these boxes or these places on the dimensional analysis, you can almost think of these as the equivalents of equal. So you could almost say, oh, this equals this. This equals this, and this equals this. That makes sense? Because that's really what's going on here. So I have known, unknown, and a ratio that I know. Okay? That equals that, or that equals that. All right, that's how these are set up. That's all we're doing with these dimensional analysis problems. So the key to this then is knowing what amount I have and what the actual label is, whether it's meters or inches or centimeters or kilograms or grams or whatever I know, and putting that equal or putting that in a ratio that's going to cross multiply. Okay? So if the unit you use is in the numerator, then that one must go in the denominator. So if and all it says is, so if I have feet here, and I want to go to meters here, here's what happens. Feet are given, meters are what I really want here, therefore I have to have feet meters. Does that make sense? And that's really all we're doing, because then when the feet cancel, I'm left with the meters. Okay? And that's really all it is. And you can see how many meters equals a foot, or how many foot equals a meter. So that's going. Okay, so that's really all the dimensional analysis is, just setting up a relationship between equivalencies that we know. All right? And vice versa on this, and you'll end up with the right one. So let's show an example of it. Let's say I want to convert 4.87 feet. Notice how many significant figures? 3. So with these, I'm going to have feet into meters. So I have feet into meters. Again, that means I'm going to have feet meters. And that's where we start. So we start all of these, not with the numbers, but with what the actual value or labeling is on this. Okay, so I have 4.87 feet. 1 meter equals 3.281 feet. Therefore, the feet cross out. I'm left with meter, and we get our correct answer, okay? Now that's a simple one, but they're gonna build, like I said. Where we're headed with this is the stoichiometry ratio. Grams to moles, moles to moles, moles to grams. Okay, it's no different than this. We set them up exactly the same, but there is some disconnect when we go from the known to these funny things like grams and moles, okay? Let's say I did 61 miles per hour into meters per second. Let's say we had a couple different conversions. So how would I go from miles per hour to meters per second? So I'm going from the English system to the metric system, and then I'm going from hours to seconds. So I have two conversions there, right? I need to go from miles to meters, and I know you need to go from hours to seconds. So that tells me that I'm gonna have at least two, maybe more, but for the most part, I'm gonna have two of these factors going on, okay? Always start with what's been given. What's been given is 61 miles per hour, right? So always put that over on your left. So I've been given 61, just 61, okay, miles per hour. There's what I've been given. That's all I'm doing. I'm setting that up as a given. Over here what I want is meters per second. That's what I want to give. So here's the thing, you can think this through. If I know what I've been given, I know what I want, it's fairly straightforward to set this up. So I'm going to have miles, and there's probably a relationship between miles and meters. Okay. Maybe it's miles to meters. Miles, meters, meters. There's a relationship between hours and seconds. So maybe it's going to be hours in a second, or seconds in an hour. Does that make sense? So that's all we do, is we establish the relationship, what's in the numerator, what's in the denominator, what do we end up in the numerator and the denominator. So here's how I set this up. Miles, hour, meters, seconds. Okay? And I'm probably gonna have two conversions in the middle of this thing. Okay? One of them is gonna be hours to seconds. I need to know how many hours in a second. The other is miles in a meter. So here I'm gonna have hours per second. And over here, I'm going to have miles per meters, okay? And so which direction did it go? What drove that was what we started with, meaning I know that there are a certain number of miles in a meter, and I know there's a certain number of meters in a mile. Again, this can be flipped either way. These ratios can be flipped either way. But in this case, it tells me that I need to have this form of the relationship because I need to have miles into meters, okay? And this relationship, again, I know that there's a certain number of hours in a second or seconds in an hour. Which form of that do I use? I use the form that puts the hour in a place that it can cancel with the second. So ultimately what happens here then, if it's set up correctly, is you cross out the relationship between those. Miles goes away, hours goes away, you end up with meters per second. It's exactly what we wanted, okay? Now you just go back through and plug in the numbers. But before we start plugging in numbers, we need to understand how to set these up. And that's, again, I think a good review. If this is a little fuzzy or if you're fine with these, fantastic. Because again, it's just simple algebraic expressions, not that complex. Okay? All right, so let's do an actual one. Let's say I want to go from 61 miles per hour into meters per second. So I have a specific example here. So, well, I've already set this whole thing up. So now all I have to go back through and do is say, well, I know 1 hour here equals 3,600 seconds. So I've got it all set up. Now I just got to fill in the chart. I know that 1 mile here equals 1609 meters. So I know that miles is going to cancel, hours is going to cancel, and I'm going to be left with meters per second. Okay? Again, fairly straightforward algebraic expressions if we set them up correctly. And it's a real working part of chemistry when we get into chemistry. Now, even if you're on your computer, listen to this. This is really important. When we deal with rounding off in significant figures, this expression is never limiting. This expression is never limiting. What limits these dimensional analysis problems is the given number of significant figures. Okay? Not the one here. That one implies 1.0000, as many zeros as you need to be the non-significant one. Likewise, when we get into true stoichiometry in the chemistry realm, these numbers are never limiting in our calculations. Okay? So, what limits, and again, on our worksheet today, I want you to make sure you keep consistent with significant figures. It's very important to practice that. Rounding off significant figures. That tells me that my answer is going to be in 2 significant figures. Because I started with only 2 significant figures. Just because my calculator has 27 significant figures doesn't mean those are significant. I only have 2. But what doesn't limit that is that one, because that looks like that's just one significant figure. Does that make sense? This is what limits my significant figures. Okay? So, oh, did I actually do it? Oh yeah, it equals 27 meters. So again, started with 2 significant figures, ended with 2 significant figures. So 61 miles per hour becomes 27 meters per second. Kind of cool, right? 3.0 times 10 to the 8 meters per second. Speed of light right there. 3.0 times 10 to the 8 meters per second. Meters per second. Okay, this is the type of table you should have at your ready working these things on the worksheet today. I provided most of the conversions that you need. But again, these are not limiting in their significance, but these are the ones that we use. These are very typical ones that you might see on the inside of a textbook, a physics textbook, or a chemistry textbook. Very common to see these on the inside. Again, here's your temperature, enthalpy. Really, enthalpy, I don't know why we have BTUs. We don't use BTUs anymore. It should be kilojoules and kilocalories. Those are the 2 big ones that we'll get into when we get to thermodynamics. Pressure, we'll deal with a little bit of pressure when we get to gas chemistry. We rarely use force in chemistry. Use mass. Again, we don't do chemistry in pounds and ounces. We do chemistry in kilograms and grams and milligrams. So we don't really use that. Liters, again, we don't really deal with this, but we'll do a couple of these and practice them. And again, meters and the English system does not use that much, okay? All right, your turn, go for it. Let's do a class practice together and then I'll set you loose on the worksheet. So convert 65.4 feet per hour to millimeters per minute. See what you get. Stand up when you get the right answer. No, just kidding. Stand up when you're finished. We'll do a speed in that dimensional analysis. Okay, you want to do this one together? Did you get it? Got it? What's the answer? 313? 332 millimeters per minute. Okay, everybody get it? Everybody want me to go over it? Got it? We good? Okay. What's that?
It's like 1,196,000.
That's what you got?
Yeah.
So that's not what you got?
If you convert it back, you get 65.4.
I'm confused.
Like if you punch in 1,196,35.2 million per minute feet per second, you get 65.4 back. So I know my calculations are correct, but it's backwards.
Oh, gotcha. Yeah. Cool.
But it's not.
It's not? Well, let's do it. Then we should do it. If you're not getting that, if we have disagreement here, we shouldn't get disagreement. So let's go feet per hour. Okay, so we have feet per hour. We're looking for millimeters.
I did it wrong.
Okay. Because this one needed how many millimeters per?
It's converting feet per second instead of per hour.
There you go. Because this one needs 3 conversions, doesn't it?
Yeah.
And that's the tricky part of that one, because I don't have up here, I don't have a direct conversion from feet to millimeter. I have to go from millimeter to inches and inches to feet. So there was a second step in there that the other problems didn't have. Cool. So are we comfortable with that answer?
Yes.
Okay, good, good. Okay, let's work on the worksheet together. And again, this is the practice of this. And then on Monday, we're jumping right into atoms and molecules. I'm super excited about building up the atoms, okay? We'll finally get into our first real chemistry.